Hello friends, welcome to the session on full wave rectifier. In this session, we will be discussing analysis of the full wave rectifier. As we have recorded this session on iPad, and now let us turn to the presentation software in order to discuss the analysis of the full wave rectifier. So friends, you know that this is a session on full wave rectifier in which we will analyze the full wave rectifier circuit and we will obtain some useful expressions. Friends, as you know that you are viewing this session on my YouTube channel and you can subscribe to the channel so that you can watch many other educational videos. We know that rectifier is an device which will convert the input AC voltage into DC. So AC means the periodically the current can change the direction or can reverse the direction, while DC is the current which will flow in only one direction. We know that there are three types of the rectifier: half wave rectifier, full wave rectifier and bridge rectifier. A full wave rectifier will convert the input AC signal into DC, and for such conversion it will make the use of both positive and negative half cycles of the waveform, and that is the reason this rectifier is being called as a full wave rectifier. Such rectifier can be constructed by using the two diodes, and one can easily observe that this rectifier is more efficient than that of the half wave rectifier. So let us understand the circuit diagram of the full wave rectifier. So this circuit diagram consists of one transformer and there are two diodes. So this is a step down transformer and it will consist of two diodes, diodes D1 and diode D2. Anode of the diode is being connected to the transformer secondary S1 and S2, while cathodes are connected together and a load resistance RL is being connected between the center tap of the transformer and the two cathodes of the diodes. Now when we apply the input AC can consist of a positive half cycle and negative half cycle, and you will find that during the positive half cycle the S1 is positive with respect to the S2, and therefore diode D1 will conduct and current will flow through the diode and the load resistance RL as shown in this diagram. And when S1 is negative during the negative half cycle, then the diode D2 will conduct and the current will flow through the load resistance RL again in the same direction. Therefore, we observe that the current flows through the diode in one direction only, and therefore we can say that the DC voltage is being developed across the load resistance RL. Now we can obtain the expression for the average DC output. So we know that IDC can be given as 1 upon 2 pi integration of 0 to 2 pi ID into omega t, where we will divide this integration into two parts, one from 0 to pi, another from pi to 2 pi, and therefore we can get the integration of Im sine of omega t into dt as 1 upon 2 pi minus Im cos of omega t in the range of 0 to pi plus Im cos of omega t in the range of pi to 2 pi. So if I substitute the values, then I will get Im divided by 2 pi in the bracket minus cos of pi plus cos of 0 plus cos of 2 pi minus cos of pi. Cos of pi is equal to minus 1, and therefore we will get this value twice Im divided by pi. So average DC output can be given as VDC is equal to IDC into RL, and therefore twice Im into RL divided by pi, so which is just nothing but twice Vm divided by pi. So this is our expression for the average DC output, and current through the diode can be given as IDC divided by 2. Now we can obtain the efficiency of the full wave rectifier by using this formula. It is a ratio of PDC divided by PAC, DC power at the output divided by AC power at the input. Therefore PDC is equal to I square DC into RL. So when I substitute the value of IDC twice Im divided by pi, then I will get the expression for PDC. Similarly, we can calculate the expression for power AC as I square AC RMS into RF plus RL. So IAC RMS can be obtained by using this formula under root 1 upon pi integration from 0 to pi I square d omega t, which is just nothing but 1 upon pi integration from 0 to pi Im square sine of omega dt into d omega t. And therefore I will get the value of IAC RMS as equal to Im divided by root 2 as shown in this slide. Now we can calculate the efficiency. N is equal to twice Im divided by pi square divided by Im divided by 2 in the bracket RF plus RL. And therefore we will get this expression when we evaluate and when we multiply it by 100%, then we will get it as 81.2%. So one can easily observe that the efficiency of the full wave rectifier is double to that of half wave rectifier. Also, one can easily observe that the peak inverse voltage in case of full wave rectifier is double to that of half wave rectifier, and it is twice Vm. So this is the voltage which the diode has to withstand. Whenever we select a diode for the full wave rectifier, then we have to see that what is its PIV rating. It is also possible that we can compute the ripple factor, and this ripple factor can be given by this formula. R is equal to under root I RMS square divided by IDC square minus 1. So this ripple factor is 0.482 in case of full wave rectifier. So thank you friends for viewing the session. Hopefully you have understood the analysis of the full wave rectifier. Thank you all.